Hello everyone, and welcome back to the Urban Computing Skills Lab. Today let us talk about another important topic, optimization. So what is that and why is that important? Working with urban problems, we often find ourselves in a setting when we have to choose from a variety of possible solutions. And we need to choose the best one. Best in terms of the price, or maybe in terms of performance, or maybe in terms of reliability. So we have certain criteria, and we need to make sure we choose the best what we can. And optimization gives us tools and techniques to make this kind of choice. So let's imagine an example. Say we are building a seawall to protect some industrial facilities or maybe urban infrastructure against storm surge. Just to make it clear, we're not talking about human lives here. We're just talking about some facilities that have measurable cost, measurable price, which we can talk about. So how tall the wall is going to be? Well, obviously you can say the taller the better. But we clearly understand that we're limited in our capacity of building it as tall as we want. Obviously, we're not going to end up building it like 700 feet tall, as the Night Watch did, because in our case, we need something more for doing that than just imagination of George Martin. So, how tall is that? How tall is the wall going to be? In order to answer this question, we need to have some additional information. First of all, how high might be the surge? So, here, for the sake of analytical simplicity in our problem, we'll assume that the maximal height of the storm surge is during the period of the wall service is distributed uniformly between 0 and 50 feet. Obviously, it's not really a realistic assumption. In real world, the distribution will be way more complicated. But here, just for the sake of simplicity, let's take it uniform. So what happens if the wall is taller than the storm surge? In this case, wall stands for it. So wall performs its service correctly. If it's not the case, if at some point the storm surge is going to be higher than the wall, then the wall fails. And in this case, we encounter a severe loss of, say, $3 billion. But only in case if the wall fails. So now if you build the wall 50 feet high, it will certainly stand for any surge we can encounter. And it will save us $3 billion. But on the other hand, this type of construction might be quite expensive. So let's imagine how expensive it is to build a wall of a certain height. Let's assume that the construction cost is proportional to the square of the wall height. And the proportionality coefficient is going to be $1 million. So if we're going to build a wall 1 feet high, it will cost us $1 million. But if we're going to build a wall 10 feet high, it will already cost us $100 million. Now the higher, the more expensive it's going to be. So now what is the balance between our construction cost and the potential savings or potential loss from the wall failing? So the projected losses, and this is the function we're going to minimize. This is our utility function, so-called. It contains two parts. First, our obvious loss of H squared $1 million, which we spent for construction. That's the money we lose anyway, no matter whether the wall fails or makes its service well, does its service well. The other part comes from the probability of the wall's failure. And this probability is going to be 50 minus h divided by 50 if we recall what kind of distribution we're considering. So that's the probability that the actual storm surge at some point will be higher than the wall we built. If that happens, in this unfortunate case, we lose $3 billion. And our projected loss is the probability of the loss multiplied by the amount of the loss. So this is the function we're trying to minimize here. The construction cost plus the projected loss. I mean, obviously, if we are just building one single wall, we might try to be overprotective. But imagine that we are building like hundreds of them all over the country. In this case, we can pretty much deal with averages. This wall will fail. Okay, we'll lose 3 billions, but we save tens of billions on the construction. So this wall will fail, but other walls won't. So here we lose, but here we don't. So in this case, we are pretty much good with the averages. So now imagine that that's our case, and we are trying to minimize the average expected loss. This is our function. If we rewrite it, it's going to be h squared minus 60h plus 3000. That's our objective function, and let's try to minimize it now. In this specific case, this can be done pretty easy with a simple analytic trick. First, let's visualize the function. So as we see, it's the highest. It has the highest value. If h is 0, in this case, the wall protects us from nothing, and we always encounter a loss of $3 billion. If the wall is 50 feet high, then we never lose anything because it protects us against any possible surge. However, the construction cost is $2.5 billion, and it's also pretty high. And we see that somewhere in the middle, somewhere in between, we actually have the lower projected loss. And it has the bottom peak somewhere around 30. Now let's try to figure out what this number exactly is. For this purpose, let's transform the the left-hand side. Let's transform the left-hand side in the following way. Let's represent it as a sum of h minus 30 squared plus 2100. As we can easily see, this term is never negative. It can be positive. It's usually positive. And sometimes it can be 0, specifically if h is 30. So if h is 30 is 0, otherwise it's positive. So whatever is h, if it's not 30, is going to be higher than 2100. And if h is 30, it's going to be exactly 2100. So based on that, this function has a minimal value if h is 30. That's our solution. And that's pretty much what we see from the plot. This was pretty easy. However, this trick works only if our objective function is quadratic. But it's not always the case, right? So sometimes it might be quadratic, sometimes it might be more complicated than that. So what if, for example, it contains an exponent, or something even worse from the analytic standpoint? So in this case, we need to employ some quantitative techniques of figuring out where this optimal h should be located. So let's consider a general case. Well, a general function, objective function f, function of x, which we're trying to minimize or maximize. So we're trying to find x such that f is going to be minimal or maximal. F is pretty arbitrary, but we need some assumptions of what kind of function it could be. And the assumption we're going to put is that f is smooth, meaning that in every point x0, it has a finite derivative that changes continuously with x0. If you're wondering what derivative is, I would certainly suggest you refer to the basic course of calculus, but just in a few words. So derivative is a limit point of the following ratio. In the numerator, we have the change of function between considered point x0 and the nearby point x1. And in the denominator, we have the difference between those 2 points, x1 and x0. And we take the limit when x1 tends to x0. So when this nearby point is as close to x0 as possible. So that's pretty much the definition of derivative. And for now, let's assume that the derivative exists, and it continuously depends on x0. And let's get back to our function. Let's visualize it for a second, and let's see how the plot looks like and what the plot actually can tell us. At every single location, this curve has a certain direction. And this direction is pretty much defined by the direction of the tangent line in this location. And the existence of the tangent line is directly connected with the existence of derivative. But I will talk about that just in a few seconds. So in different points, the direction of the tangent line might be different. However, as long as it's not horizontal, this means that from one side, on one side of this point, the values are lower than the value of the function in this point. And on the other side of the point, the values are higher. Or the other way around if the tangent line goes down. So what it means for our optimization problem is that this specific point can never be a maximum or a minimum of this function, because regardless of what this point is, there's always a point either on the left-hand side of it or on the right-hand side of it where the function is bigger or smaller than this specific value. So any point where the tangent line is not horizontal is not our solution. However, sometimes tangent line might apparently become horizontal, like here, for example, or here, or here. So those are special types of points where our function can change direction, meaning that it can decrease before this point and start increasing afterwards, or increase before the point and start decreasing afterwards, or decrease and then start increasing. In those specific points, the function can have at least the local extrema. Not have to, but can. What does it mean, local extrema? Local minima or local maxima? If we're talking about local maxima, for example, here, it means that for any nearby location, the value of the function is lower than here. If we're talking about local minima, it means that in any nearby location, like here or here, the value of the function is higher than its value in this specific considered point. So the necessary condition for the point to be the point of local extrema, minima or maxima, is that this tangent line is horizontal. If it's not, then the point is for sure not the point of local minima, nor local maxima. So now what do we need to have for this line to be horizontal? What does the incline of this line depends upon? This incline, specifically the angle between the tangent line and the horizontal line, let's call it alpha. This angle alpha is directly related to the value of the derivative in this considered point. Specifically, the tangents of alpha equals to the value of the derivative. So if we want this alpha to be 0, if we want the tangents to be 0, then we need to have the derivative to be 0 as well. This means that if we want the point to be the point of local minima or maxima, the derivative of the function at this point is going to be 0. It's not the sufficient condition, so if you have derivative 0, this point might not be the point of local maxima or local minima. However, if the point is the point of local extrema, then derivative is going to be 0. So, now how do we solve our optimization problem? Obviously, we need to look for those points. We need to look for those points of local extrema. But even if this point is indeed the point of local minima, and we're looking for the minimal value of the function, for the point where the function has this minimal value, it doesn't mean that it's here. For example, consider this point. Indeed, this is a point of local minima, so all the values of the function in the nearby points are higher than that. But at some point, the function might change direction again. It might go even lower than that. So in some other point, the value of the function might be even lower. So it might be the point of the local minima, but not of the global one. So now what we need to do, we need to consider all the possible points of local extrema, where we have the value of derivative going to 0, compare value of the function in those points, and also compare those values to the value of the function on the end of the interval where we consider it. Because on the end of the interval, the function might also go up or down, and those values might actually exceed the highest maxima encountered in the middle of the interval. So, for example, this is the highest maximum we have, right? So this value is higher than this and higher than this. However, it's still lower than the value on both ends on the interval. So that's not the global maximum, it's only the local one. So in order to make sure that's the global one, we need to compare all those values. Value here, value here, value here, and also the values on the end of the interval. So now let's revisit our previous example with this new optimization technique, looking for the local maxima and compare, actually local minimum, because we are minimizing the function, and comparing those values. So the function on the left-hand side, if we take a derivative of it, we end up with a linear function like that. The derivative of h squared is going to be 2h, the derivative of 60h is going to be 60, the derivative of a constant is 0. So the derivative is 2h minus 60, and in order for this point h to be a point of local minima, we need the derivative to be 0. There's no guarantee that if it's 0, it's indeed going to be local minima, but that's a necessary condition. So and that is the only point that satisfies this necessary condition. That's going to be 30, right? So if 2h is equal to 60, then h is 30. So again, we get back to our original solution, which is not surprising, of course, but we get it in a very simple way here. And if we look at the values of the function on the ends of the interval, if h is 0, it's 3 billion. If h is 50, it's 2.5 billion. And in this point of possible local extrema, it's 2.1 billion. So it's indeed the lowest possible value of the function. So it's indeed the point of global minima, which we look for. We found it now. So it looks pretty well for the single variable function like that. And this technique also works for the multivariable functions, for the multivariate functions. So in the multivariable case, what we need to do in order to look for local minimas or maximas, we need to require that all the partial derivatives of the function by all the variables in this specific considered point are 0. So the function encounters a so-called a plateau in any direction. That's not a sufficient condition, just as it was not a sufficient condition for the single variable function, but it's a necessary one. So we look for those points, and we compare values of the function in all of them, and also we look at the values of the function on the boundaries of the domain of the function definition. So let's consider the following example. Say we have a certain number of locations for residential houses, and we need to find such a suitable centroid location so that we can put an energy supply station there. For example, we can put it here, or here, or here. So no matter where we put it, assume that the loss of energy for each specific house is proportional to the square of the distance between the facility and the house. So in this case, as you can imagine, our utility function will be the cumulative loss of energy. So we want to put the facility in such a way that we minimize the loss of energy to all the buildings. So in this case, what we want to minimize is a cumulative square distance between the facility and all the locations of the residential houses around. So we want to minimize this function, where x asterisk and y asterisk are the coordinates of the facility, and x, y, yi are the coordinates of the residential houses. So I want to minimize that. And that's the function of two variables, x asterisk and y asterisk. In order to minimize it, we need to look at the partial derivatives of this function that we're trying to minimize by x asterisk and y asterisk. Luckily for us, due to the analytic simplicity of the function, specifically this is again a quadratic function, just the multivariate one, the derivatives are linear and they look like that. So the derivative by x asterisk is the sum of double differences between xi and x asterisk, and derivative by y asterisk is pretty similar. It's just the sum of differences, double differences between yi and y asterisk. Now, if we want those to be 0, then it's easy to see that x asterisk satisfies this equation. We just sum up all the xi's on one end and all the x asterisks on the other end. We have them n times, where n is the number of residential houses. And the same for y asterisk. Once we solve those equations, we have that x asterisk is simply the average value of all the x coordinates of all the residential houses, and y asterisk is simply the average value of all the y coordinates of the residential houses. So the solution is as simple as that. We just need to put the energy supply facility in the middle in terms of both x coordinates and y coordinates. So this was easy, but this is easy as long as the function is easy, as long as the analytic shape of this function is manageable for us. Again, if that's something more complicated, we need some more magic here. And luckily there is such a magic, which is called numerical optimization methods. So let's consider an arbitrary function of the multidimensional variable x. So x here is a vector, which contains multiple dimensions or multiple variables, if you prefer. And we are looking for minimal or maximal value of this function and the value of x, which supplies us with this minimal or maximal. So there's a whole family of the numerical methods which allow us to approach this minimal or maximal point in an iterative way. So what we do, we start from an arbitrary point, like x0, somewhere in the domain of possible values of x. And by the way, those blue curves, they are level curves or so-called geodesic curves. Maybe if you like hiking, or if you ever go on a hike, when you look at the map of the trail, you see those curves. They show you the points of the same attitude. So for example, here you're on 2,000 feet. And here you're on 2,100 feet. And here you're on 3,000 feet. And here you reach the summit. Right? So here we show the values of our function in a pretty similar way. So imagine that the value of the function is the attitude. And, well, the location is where you are. So now, if you try to, for example, minimize the function, then you're looking for a point with a minimal attitude. So how do you do that? Intuitively. Like right now you're here in point x0. So you're looking around, trying to make a step right, or step forward, or step backward, or step left. in such a way that you're going down. So you want each of your steps to bring you down. And then at some point, you think that you might reach the bottom, right? So here we do the same thing. So we start from a certain initial value of x, x0, and we're looking for a small step which brings us to the value x1 when the function is lower. Then we make a next step which brings us to x2, and the value is even lower than that. And then we go ahead until we can't make any further step. At that point, we believe that we reached the minimum, or at least a local one. There's no guarantee we'll reach the global minimum, because maybe somewhere there's a lower location. But at least we reached what we could reach from this neighborhood. So this is the idea of the method. Now the question is how we make those small steps, how we select the direction for our step. Here we employ the concept of the gradient. And gradient is a vector which incorporates all the partial derivatives of the function by all the coordinates in a specific location. So we take the partial derivative by the first coordinate, by the second coordinate, by the nth coordinate, and we put them together into a vector. So this vector is called gradient. And its role is to point out the location of the fastest growth of the function. So the function grows the fastest in the direction of the gradient. So if we are looking for a maximum, we just need to move towards the gradient. We just need to move towards the location of the fastest growth. On the other hand, if we are looking for a minimum, then we need to move in the reverse direction. So we need to move in the direction of the minus gradient, in the opposite direction. So now what we do, once we have the location xk, in order to find the next location xk plus 1, we look for something like that, xk minus gradient multiplied by a certain value. So what is unknown here is this value, gamma k. There's a whole bunch of methods to pick up one, but the bottom line is that we are looking for such a coefficient that minimizes the value of the function in the new location xk plus 1. So there's a whole bunch of methods which work that way. They're unified under the umbrella of the family of gradient methods because they all deal with a gradient here. They differ usually in the way we select this gamma and in some other specific details. But generally, the idea of the gradient methods is like that. So we iteratively improve the value of the function, improve in the direction of where we want it to go, up or down, by making a small step towards the gradient vector. Now let's look how it works in practice. So now let's consider the same problem as we did before with the residential houses and the energy supply facility located somewhere in between, in the middle. But let's assume that the energy loss is proportional not to the square distance between the facility and the house, but to the regular distance. So the longer, the more we lose. Or maybe it's not a loss. Maybe we're now talking about the cost of the cable to put. In this case, obviously, the cost of the cable will be just proportional to the regular distance, not the square distance. This actually changes the analytic shape of our function, makes it a little bit more complicated because now we have the square root over here. And we need to minimize this type of function. How we do that? It will be rather complicated to do it just looking at the analytic shape of derivatives and trying to solve the system that we easily solved before, because it won't be linear anymore. So now, let's try to employ the numeric gradient method to look for the best possible solution. So we do it in Python. So first of all, we make sure we load all the required libraries here. And now we that's actually the kitchen behind the curtains of how I generated the locations that you saw on the slide. So we fixed the random generator at some point, just to make sure that every run you have the same result. We create the random values for x and y, and we put those values, those points on the screen now using plot. Now the following code is supposed to implement the gradient method. Actually, the method is already implemented, so there's nothing we need to implement by hand here. The method is implemented here in the function minimize that Python supplies to us. What we need to implement, though, is a specific objective function that we consider, which is the sum of square roots of the distances, of the square distances, so basically the sum of the distances. And we also need to supply the gradient for this function, because as you remember, the gradient methods heavily involve the gradient itself. So we need to know the way how to compute gradient in each specific location. So this is the function which supplies the gradient. Now we start from plotting all the locations one more time. We start with just arbitrary point, 0, 1. We plot the point 2. And here's the function which will visualize the result of each iteration. So it will start from the previous point and draw the line to the next point. Draw the line to the next point. And it will also print the current value of the coordinates. Finally, we call the minimize function that deals with the arbitrary objective function and its gradient. It's applied here. Here we select which specific method of the family of gradient methods we go with. And here we set up some of the parameters, like whether we want to display every iteration and what kind of function will do that, what kind of error we're going to go with, because the gradient method should stop at some point. It might be the case that we'll find an exact location so that no further step is possible, but usually there will be always a small, tiny step possible towards the direction of the minimum. So we just get closer, closer, and closer to the minimum point, but we never reach it, really. So at some point we need to stop. And the criteria of our stop will be that the new step is smaller than a given point, than a given tolerance. So as soon as the steps become smaller than that, we stop. So that's how we set it here. Now once we run the function, what it gives us the sequence of the locations, and it visualizes our path from this first initial point, 0, 1, to the next better point, to the next better point, to the next point. And here we already stop because the next move, the next shift will be smaller than our tolerance. So this is the location for the facility if we want to minimize the cumulative sum to all the residential houses around, not the square sum. If it will be the square sum, the location will be slightly different. So this is the way how it works in practice, and this is the way how you can code it in Python. So please feel free to, and certainly you will have this notebook together with the slides. You can access it, and feel free to adjust the code for your specific problems. Good luck with that. And thank you so much for your attention today.